Sometimes we face a strange situation in STAAD.Pro where the modal frequency or frequencies are reported as 0. Now, what does this mean? And is it a good thing or a bad thing? Let us find out. But before we go forward, let us take a moment to welcome anyone who is new to this channel. And we also request the newcomers to hit the subscribe button and join us in this wonderful journey of exploring structural engineering. Let us consider the single degree of freedom system with mass m, which is supported by a massless member of stiffness k fixed at the base to set the context of the discussion. Now let us pull the mass from its mean position or the minimum potential condition to a distance a and hold it there. Now, if we release the mass m, the mass tries to go back to its minimum potential energy condition and hence goes vibrating about the mean position. Now, we have considered the massless member to be an ideal frictionless member, and thus theoretically the mass would continue in this vibration mode forever. However, realistically, the mass would regain its mean position because of the internal damping of the STAAD system. Now, if we plot the displacement of the mass from its mean position against time, we will get a harmonic curve like this. At time t equal to 0, we will have the maximum displacement A. Remember, this is the instant of time when we release the ball to vibrate about its mean position from its maximum displacement position. We have only plotted 2 1/4 displacement cycles in this figure. The dotted arrow indicates that the curve continues with time, as this is an idle no damping case. The time taken to complete one cycle is called the time period t. Now, the number of time the mass m passes a specific point during vibration, signified by a constant displacement in the displacement time graph in 1 second, is called the frequency of vibration. So this means that for frequency to exist, the mass needs to pass through a specific point in vibration multiple times. Like in this case, if we consider the mean position of the reference points, we can see multiple time instants when the mass has passed through the mean point. But this also implies that a frequency of 0 would mean that the mass will not pass through the point at all or only once. So what could be the situation when the frequency of a structure can be 0? Before we answer that, let's spend some time to check the equations available for calculating frequency. The first equation available says that the frequency is the reciprocal of time period, which means that for frequency to be 0, the time period has to be infinite. The second equation relates the frequency to the mass and stiffness of the structural system. In this equation, we find that for frequency to be 0, the stiffness of the STAAD system needs to be 0. And both equations actually tell us the same thing. Let us find out what. Now let us consider the STAAD system being fixed to a roller instead of being clamped to the base as shown before. So what would happen if we intend to give it some initial displacement to make it vibrate as before? Well, the STAAD system will be displaced towards the right as it is sitting on a roller, never to come back to its initial position. So this makes the time period to be infinite and the frequency to be 0. And if you look carefully, there is nothing that can pull the mass back to its original position, which means that the stiffness of the STAAD system is 0. So now we can see that the time period being infinite or stiffness being 0, which means that the frequency of the system is 0, is an indicator of inherent instability in the structural system, and thus the structural system will move in a rigid body mode. And the frequency being 0 indicates that the structural engineer has specified masses in a structural model in the unstable direction, and thus he would need to fix this immediately. But before we go forward, are you getting value out of this channel? If you are, please press the like button right now. Done? Good. Now let us go forward. Now this is the model of the same unstable structure that we have just seen. Now if we go into the text editor and we go to the support specification, you will see that we have defined the roller in the x direction using the fixed but command. Now, if you go to the load specifications, you will see that we have defined the mass which is capable of vibrating in the x direction. Now, let us go out of the editor and let us run the analysis. Now, once the analysis run is complete, let us go into the output file and let us see the Eigensolution results, and we can see that the frequency of the structure has been reported as 0 as expected. The period comes out to be a big number, but it doesn't come out to be infinity as we might have expected. Well, the reason is that the computational systems cannot handle division by 0 situations, and thus the unstable direction has some weak springs added to it, which is the reason why we get a non-zero value of time period. A reminder that a zero frequency mode is an indicator of an unstable direction in the structure that the structural engineer needs to take care of. Now let us look into a more practical model. We have defined the mass model of this structure in a reference load case. So if we go to the reference load definition, we have a mass reference load case here, and if we expand that mass reference load case, we can see that we have defined the mass components of that structure in that particular load case. Now if we go into the primary load case, we see that we have a primary load case as well, where we have defined the modal calculation requested command. Now the modal calculation requested command is an instruction to the program to do the eigensolution of the structure. Okay, now if we run the analysis, and as the analysis gets complete, we can see that it reports 100 warnings that has been detected in the process of the analysis. Now what are these warning messages? Well, to find that out, let us go into the output file, and we can see that in the error list, we can see those warnings, and we can see that all those warnings relate to zero stiffness and instability, which is an indication of a potential instability that is existing in the model. Now, let us minimize the error list, and if we double click on the Eigensolution here, let us scroll down a bit to find the Eigensolution results, and we can see that the natural frequency reported for the default 6 modes are 0, which is a definite indication of existing instability in the structure. We also see that there is a warning message about rigid body modes being detected in the model. So these are definite indication of an inherent instability existing in the structural model. So how can we definitely confirm whether the structural model has instability problems or not? Well, the zero frequency report in itself is a definite proof that the structure is unstable, but let us check the other aspects of detecting instabilities in the structure as well. So let us go into the text input file. So let us go into the text input file here, and if we go into this load case here, let us deactivate the modal calculation requested command by putting a star before the command sign, and then we define a static load case with self-weight components in all the 3 directions. So we have self-weight in the x direction, self-weight in the y direction and self-weight in the z direction. Now, once we have done that, we have created the static load case. We go out of the text editor. We are prompted to save the changes. So we save those changes. And then we press Control F5 to invoke the analysis. Now, one of the things that we need to understand is if the structure is stable, then the equilibrium check will be satisfied. So that is what we are going to check. So we are going into the post-processing mode to check whether the equilibrium conditions have been satisfied or not. To find that out, we go into the reactions option and expand the statics check table, which is nothing but the equilibrium check. The first row, now remember that we have only one single load case. So the first row indicates the applied loads of that load case. The second row indicates the reactions that are being developed because of that load case. And the third row indicates if there are difference between the applied loads and the reactive loads. Now, if there are difference between the applied load and the reactive loads, then the structure is not in equilibrium. The equilibrium check has not been satisfied, and which would indicate a potential instability existing in the structure. Well, in this case, we find exactly that. There are substantial difference values that we can see, which is an indication that the structure is unstable, or rather a confirmation that the structure is unstable. There is yet another confirmatory check that we can do to check whether the equilibrium or the structure is in equilibrium or not, and that is if we go to the displacement tab, if the structure had been stable or in equilibrium, the displacements would have been small. But if we check the displacement summary and check the maximum values of displacement, we can see huge values of displacements, which is another clear indication that the structure is unstable. So now we have to identify where the problem in the model is. So let us go back to the modeling mode and try to find if there are multiple structures in the model. Multiple structure check generally gives a clear indication of independent structures existing within the same model in case the structural engineer is not aware of it. Note that the mere existence of multiple structures in a model doesn't indicate a problem, as the multiple structures can be intended by the structural engineer. For example, the structure can be a building with an expansion gap as required by the code. That would be a valid case of why multiple structures can exist in the same model. Now let us go to Utilities, Structure Tools, and then Multiple Structures. Remember that this is going to be our primary tool, that is the structural tools. This is going to be our primary tool in investigating the structural instability problems. So structure tools, multiple structures, and we can see that there is only one structure that exists in the model. So multiple structure does not really indicate any problem in the model. Now let us go to the select option, select the plate cursor, and let us select the whole model. Now, if there are existing plates in the model, they would be highlighted by the selection, and we can see that there are indeed plate elements in this particular structure. So let us go to the loading mode to see the view a bit more clearly, and we can see that the structural engineer has created the staircases with the help of plate elements. Now let us go for our next structural integrity check, the beam plate connectivity. Now that we know that there are plates in this model, so let us go for that particular check. So structural tools and beam plate connectivity check. Now one thing before doing this check is that the multiple structure check does not take into account the plate elements, and this might be one possible area where we can investigate the cause of inherent instability. So let us click on the beam plate connectivity, and we can see the check has been performed, and lo and behold, there seems to be a lot of cases where there are beam plate connectivity problems. We have checked on the radio button to highlight both the beam and the plate which has improper connectivity. And if I scroll through the list, the relevant entities would be highlighted in the viewing area. Now, let us do this. Let us select the first pair of the problematic beam plate entities, and let us view those entities in more details. So we go to the new view and display view in the active window to highlight or to see or to view only the highlighted entities. So now that we can see that the troublesome beam and plate, which has a connectivity problem, is being displayed exclusively on the screen. Now let us quickly turn on the beam number, turn on the plate number, let us turn on the node points and turn on the numbers. Now let us select the plate cursor and hold it over the plate, and we can clearly see that there is a connectivity problem here. Now let me explain this in details for the sake of those who have not understood. So, but before I do that, let me maybe take off the support display by pressing Shift plus S so that we can stop displaying the fixed support. Now we can see the beam and the plate entities very clearly. Now the beam is created between node number 678 and 848. And we can see that the plate has been connected between node numbers 961, 963, 965, and 966. Now, it is very clear that there is no common node that exists between the beam and the plate. To have a proper connection in finite element analysis, it's very important that there is a common node between the entities. Now, though 848 appears to lie on the plate, but that node number does not form a part of the plate incidences, and hence they are not connected. So let us go back to the full view of the structure again. So go back to the view option, click on the display whole structure, and let us remove the plate numbers, let us remove the beam numbers, let us remove the node numbers, let us remove node entities. Now, based on what we have understood, it would mean that all the proper beam plate connectivity problems is of the same nature and has led to a situation where the plate element resembling the steps on a staircase are plainly hanging in the air and hence unstable. And thus, this modeling problem has led to the zero frequency problem. Modeling errors are the primary causes of zero frequency problem, which is an indication of existing instability in the structure and the masses being defined in the unstable direction, and hence the structural engineer needs to take care of that. But what if the modal frequency is non-zero but is small? Well, a near zero frequency like 0.001 Hz is an indicator of instability, but something like a 0.4 Hz is not necessarily an issue, but has to be studied in context of the structure. Let us, for example, consider this structure. This looks to be quite a heavy building. Now, we have already run the modal analysis of this structure. So let us look into the frequency report. For that, we go into the post-processing mode. Yes, for the earlier structure, we had checked the frequency report in the output file, but you can even check for the frequency report in the post-processing mode. To check that in the post-processing mode, we need to go to the Dynamics tab and go to this table at the top, which would display the frequencies of the modes. We see that the first four modes report a frequency of 0.37 Hz, which does not really correspond to this structure, does it? As frequency is the measure of energy required to vibrate the structure in that mode, 0.37 Hz appears to be quite low, and that too for the first four modes. So I have created another file to create a static load case with the self weight in all the direction and see if there is inherent instability reported by the equilibrium check. Now, I have also run the analysis for this particular model. So let us go into the post-processing mode directly and go into the statics check table. And in here, we can see that the difference is either 0 or very, very insignificant, which we do not need to consider. So this means that we do not see any problems in the equilibrium check, and which also means that the structure's load is finding a way to be transferred to the supports. Now let us check for another check for instability, which is the deflection check. And if we go to displacements and if we check the summary of displacements, we can see that the deflections are reported as nearly 2 meters, which is absolutely inconsistent with this structure. So this is a clear indication that something is wrong with this structure, even though the equilibrium check is satisfied. So let us go back to our original model and let us animate the mode shapes. So to animate the mode shapes, we go to the animation option, click on the mode, click on apply, and we need to click on OK. So once the mode shape is animated, what do we see? Well, the first mode indicates that only one column is moving as a free cantilever while the rest of the structure is not excited at all. Now, this is a clear indication that the column is not connected to the rest of the structure. Now, let us go to the second mode and let us see what does it display. So second mode, and we see that another column is being displayed. Now it's still being displayed. So we now see that a different column is displayed, which again is swaying independently while the rest of the structure is not excited. So that means that column 2 is not connected to the rest of the structure. However, the third mode. So the third mode, let us wait for some time for that third mode animation to be generated, and we would see that third mode is nothing but it shows the first column in a different mode. And for mode number 4, we see that it is a different mode for the second column, which was showing freely. Now we understand the reason of why the modal frequencies were so low. You guess the reason? Well, it does not really represent the frequency of the structure, the whole structure in vibration. Rather, it is the frequency to represent the free vibration of the free columns, which is not connected to the structure. And that's why the frequencies were so low. But if we go to the mode number 5, only in this mode, we will see that the participation of structure has begun. So the first 4 modes were the modes that represents the free vibration of the columns, the 2 columns which were not connected to the structure. So in this case, the low frequency of the first couple of modes is a result of faulty modeling, which the structural engineer needs to take care of. One needs to read the frequencies in context of the structure to sense the problem with the results. Animating the mode shape is one good way to detect problems, if any. And we are in the final aspect of our discussion today. We are looking at a pipe rack structure, the structures used for supporting pipes. Now, when we do an eigenvalue solution of the structure, which I have already done, and look at the frequency values, that is, if I go into the post-processing mode, and if I look into the frequency values, the modal frequency of the first mode is 1.060 Hertz. This value looks to be corresponding to the structural model, so I don't see any real problem here. Now let us activate the mode shape. So let us go and animate the mode shape. Click on apply and click on OK. Now what do we see? Well, we see that the whole structure is not excited simultaneously in the X direction as I had expected. There seems to be some local fluttering in the middle portion of the pipe rack. This might be a case of inappropriate stiffness, which might be the result of weak members in that region or weak connections of this portion to the rest of the structure. But this may be intended by the structural engineer as well. So we do not really know, and only he can say whether this behavior is an expected one. So I hope you have liked the presentation today, and I hope I had been able to deliver some value. So thank you for listening. That is all that I have today. If you have liked this one, please do hit the like button, and I will see you in the next one. Till then, bye bye and keep well.